a linear regression can be understood using a very simple equation, and this equation is y is equal to mx plus b. Understand that this is the equation that you might have seen in your college life, you might have seen in your school life. So here y is the variable that you take on the y-axis, m is the slope, b is the intercept on the y-axis, and x is the independent variable. So to give you an example, let's say that I want to understand how happy I am. And my happiness depends on whether my parents give me pocket money or not. So I can say y is my happiness, and that happiness, it depends on x, where x is the pocket money given by my parents. So I can say my happiness is a function of my pocket money. Now here m is the slope. The slope tells us how much will I be affected by x. So when x changes by 1 unit, what would be the change in the y variable? That is what m stands for. Okay, let us go ahead and let us explore this equation in terms of an example. But before I go ahead to that example, I would like you to understand how do we work with linear regression in the real world. So we usually have a training data set. The training data set is what we show the machine. After we show the machine the training data set, we go ahead and we apply a learning algorithm on that training data set. The algorithm can be anything. It can be linear regression, it can be naive Bayes, it can be any other supervised machine learning technique. And then we keep a hypothesis in mind. For example, the hypothesis that I may have in mind is that the size of the house goes ahead and affects the price of the house. This is something that you would have seen very often. You would have noticed that 1 BHK has a lower price as compared to 2 BHK, and 2 BHK has a lower price as compared to 3 BHK. So the hypothesis that we have in mind is that the size of the house goes ahead and affects the price of the house. So the price of the house becomes the dependent variable, and the size of the house becomes the independent variable. Dependent variable depends on the independent variable. So consider what I will get here. So suppose on the x-axis, I have the size of the house, and on the y-axis, I have the price of the house. What do I observe? I observe that as the size of the house increases, the price of the house also increases. All these red points that you see, these are the points which are the real points. They are the actual points. So the red dots show you the actual points that when price of the house was 500, size of the house was 500, the price of the house was 200. When size of the house was 1000, then I go here and I check the price of the house was about 420. So each of the red point depicts the actual situation that is there in the housing market. Now, I want to show these red points to my machine as a training data set, and using those points, I want to ask my machine to give and predict a model. This blue line that you see is what the machine predicted for you. So the line that passes through these actual points, that line is called the regression line. Of course, the line cannot pass through each and every point, right? That would be so much overfitting of the model. So what happens in this case is we ask the machine to give us a best fitted line taking into consideration these points. So the line tells me that there is an upward relationship between the size of the house and the price of the house. As the size increases, the price of the house also increases. Consider this. This is the actual example. So when size of the house was 2104, the price of the house was 460. When size of the house was 1400, the price of the house was 232. Size 1500, price 315. Suppose I have a lot of such observations. Suppose M is equal to 47, which means there are 47 such observations that I want to go and give to my machine. Now, X stands for the input variable or the independent variable. In this case, the independent variable is the size of the house. The independent variable tells us what is going to help me understand the dependent variable. It is also called as the feature. Y is the dependent variable. The dependent variable is also called the target. These are the terms you will see very often. So X becomes the feature, Y becomes the target. Each observation that I have, for example, 2104, 460, these are my training examples. Now, the aim of the machine is to go ahead and to prepare a model between Y and X, and that model will appear something like this, theta naught plus theta 1 X. So it is just telling me that, look, the value of Y depends on the value of X. If you increase X by 1 unit, Y will increase by theta 1 units. Okay. Now, what is linear regression? So linear regression basically allows us to build a relationship between multiple features, which means multiple independent variables, to estimate a dependent variable. So in this case, I should not only have one independent variable, I can have more than one independent variable also. Like for example here, my price of the house depends on area, it depends on number of bedrooms, it depends on number of bathrooms. This is obvious. We have seen this in the real world. If you have more bedrooms, you can sell your house for a higher price. If you have less bedrooms, it will be sold for a lower price. Now, these area, bedroom, bathroom, these all independent variables form my X, and the price that forms my Y. So basically, what do we have? Well, we have a list of X's, X1, X2, X3. These are my features. These are my independent variables. And these independent variables determine my dependent variable, which is Y. So something like this is a general form of writing the data set. Now, once you have this data set, you understand that there are two things happening. One is the feature. The other is the target variable. X is the feature. I have three features here, X1, X2, and X3. Y is the target variable. Now, I want to go ahead and I want to build a linear regression out of it. The linear regression in general form can be written like this. So I have my Y variable, which depends on X0, X1, X2, and so on. This is the way of writing the linear regression. Now the question is, can I go ahead and understand which is the right linear regression? Can I understand how to go ahead and formulate this linear regression in the best way possible? How to go ahead and get the right betas to write this linear regression? Well, yes, we can go ahead and do that. And how do we do that? We can go ahead and do it by minimizing the error. Now you may ask, what is the error term? Well, the error is the difference between the actual values of Y and those predicted by your model. So consider this, for example. In this case, Y is this value, blue value. Blue tells me the actual value of the Y for a given X. The yellow line, it tells me what my machine went ahead and predicted. The gap between the two is the error term. So at any point of time, there will be some error that the machine would be committing. Let us go ahead and see that error. So consider that blue is the point that's the actual point that is given to you. Yellow line tells you what the machine predicted. The gap, this dotted line, this is your error that the machine is predicting. The aim at any point of time is to go ahead and minimize the error. So the values that the machine predict, that is called y hat. The actual values given to you is called y. The gap between y and y hat is called the error term. Let's quickly go ahead and look into it. Now, based on the model, the value of your slope may be positive or may be negative. For example, if I say a relationship between pocket money and happiness, I know that that relationship is positive. The more the pocket money, the more the happiness. So I would assume that the value that my slope will take, the value that M will take, will be positive. M tells me how Y is affected when X changes. So because when pocket money increases, my happiness increases, I will assume M to be greater than 0. M may be negative also. Like for example, when my exams increase, my happiness decreases. So M can be negative if X stands for exams. M can be 0 also. For example, I am not affected if, there is a holiday on Sunday or not. Maybe I'm not affected by holidays. So I can say that if X is holiday, then M can be 0. So M can be positive. If Y is positively affected by X, M can be negative. If Y is negatively affected by X, M can be 0 if Y is not affected by X at all. Now, based on this, we have got the following relationship. We have got that there is an independent variable. There is a dependent variable. The dependent variable is trying to get understood because of the independent variable. How much it is helping is determined by the slope. The slope is M. Slope can be positive, negative, or 0. Our aim is to determine or predict the value of the dependent variable. The value that we get from prediction, that is called the Y hat value. Now, once we have understood this, the question that we have in hand is, how do we go ahead and how do we get the best values of these M or of betas? So the aim is to get the best possible value of beta naught and beta 1. Well, we already have a formula. This formula says that beta 1 should be rho into sigma y by sigma x, where rho is the correlation coefficient, sigma y is the standard deviation of y, sigma x is the standard deviation of x. This tells us that the value of beta 1 is correlation coefficient into standard deviation of y upon standard deviation of x. Now you may ask, how is this value derived? Why this value? Why not anything else? Well, this value is derived by minimizing the sum of the squared errors. So the aim of linear regression at any point of time is to minimize the error terms. And when we try to minimize the sum of the square of the errors, this is the value of beta that the machine will give you. So this is the beta 1 that the machine will give you. You don't have to literally use this when we do Python. The machine will simply give you that coefficient value is this much, as I will shortly show you. Once you have derived beta 1, you can also derive beta naught, and beta naught is given by y bar minus beta 1 x bar. Okay. Now there is a few of the limitations that I will show you of linear regression. What are those limitations? Linear regression cannot work if the relationship between y and x is quadratic. Linear regression cannot work if your y variable in itself is discrete. For example, the example that I was giving you. When I say that I want to predict my happiness from pocket money, happiness is a qualitative variable. It can either be I am happy or I am not happy. It can only take two values. So when your y variable can only take two values, when it is a qualitative variable, or when the relationship between y and x is polynomial, linear regression will not work. In that case, we will go to different kind of regressions. We may go to polynomial regression, we may go to logistic regression, but you must understand that linear regression does not work. Okay, so let me give you some examples of linear regression before we can go ahead. So take this example. Suppose a manager wants to find the relationship between number of hours that a plant is operational and weekly production. You can use linear regression. So I want to find out the relationship as to what happens as the number of hours increase. Does my productivity increase or not? Similarly, I here know that independent variable will be the number of hours that my machine works for, and dependent variable will be my production volume. So something like this. You will give X to the machine. This is the number of hours you work for, and this will be your volume of the production. This is going to be how you can go ahead and plot different points. And then you can ask your machine to go ahead and fit a linear pattern through those points. After you fit a linear pattern, you may get something like this. So this equation tells me that as you increase X by 1 unit, which means as you increase the machine hours by 1 unit, Y, which means the number of units produced, will increase by 4.5 units. So the slope tells me how Y will change when there is a change in X. Okay, and that will be it. Now, one last thing before we can go to the coding is how do I find the best fit line for my linear regression? As I told you, the aim is to go ahead and minimize the error between what the machine predicts and the actual value of Y. And this is exactly what we are doing. So understand that Y hat is the value that the machine predicts. Y is the actual value of the machine. The gap between the actual value of the machine and what machine predicts, that is the error term. Let me just show you that. So this is how your error looks like. Y is the actual value of the machine. Y hat is what is predicted by the machine. The gap between Y and Y hat is called the error term. At any point of time, the aim of the machine is to minimize the error. But there is a problem. In linear regression, the sum of the error is 0. Then what do we do? How do I know which model is performing better? Well, we don't minimize the error. We minimize the sum of the square of the errors. So the aim of the machine will at any point be to square up the errors, sum those errors together, and go ahead and minimize that. This is called the residual sum of square. Whichever model gives you the minimum residual sum of square, that is the best model to work with. Let me now take you through one of the simple code to understand this linear regression. After today's lecture, I will go ahead and I will share this with you, and you can also practice this on your own. Okay. Now, here I'm going ahead and importing some libraries. What is this that I've opened up? This is a Jupyter notebook. We write all our Python code in Jupyter. In case you are not familiar with Python, just for now understand that these are some of the libraries that help us with visualization, that help us with some of the things like addition, subtraction, going ahead and finding mean, median, mode. These libraries help us do that.